To expand this binomial, 3m plus 1 to the 4th power, without actually having to multiply it out 4 times, we can use what's known as the binomial theorem along with Pascal's triangle. The way that I set up a problem like this is by showing the information in a table, because I know I need 3 things to come up with each of the terms in the expansion. I need the coefficients from Pascal's triangle. I need the first term to start at the highest exponent and decrease, and I need the second term to start at the lowest exponent and then increase. And if I put all those things together, I'll get the answer for each one of the terms in the expansion. So I kind of set up a table like this and go from there. Now, to know the coefficients that you need from Pascal's triangle, you use whatever the exponent is outside of the binomial. So in this case, if I go to Pascal's triangle, it would be this row right here. Those are the coefficients that I want, because that's the 4th row where the 4 is in the second position. So I list those out. It's 1, 4, 6, 4, and 1. Then, like I said, the first term, which in this case is 3m, it should start at the highest exponent, which in this case is 4, and then it should slowly decrease from there until it's at 0. So 3m to the 3rd, 3m to the 2nd, 3m to the 1st, and 3m to the power of 0. And I'll figure out what each one of those is in a second. Now I go on to the second term, which in this case is a positive 1. The second term should always start at the lowest power, which is 0, and then it will increase 1 until it gets to the highest. And so I got 1 to the 2nd, 1 to the 3rd, and finally 1 to the 4th. Now back over here, when I said I was going to work this out, the fact that 3m is in parentheses and the exponent of 4 is on the outside means this is 3 to the 4th power and m to the 4th power. Well, 3 to the 4th power gives me 81, and so this would be 81 m to the 4th power. This one would be 3 to the 3rd power, which is 27, and m to the 3rd power. This one would be 3 to the 2nd, which is 9, and m to the 2nd. 3m to the power of 1 means it's still just 3 and m. And then this one, anything raised to the power of 0, that answer is automatically going to be 1. Now over here, I know I don't really need to list them out, but just to show you that I would go through it if it were not a 1 on the inside. 1 to the power of 0 is 1, 1 to the power of 1 is 1, 1 to the power of 2 is 1, 1 to the power of 3 is 1, and 1 to the power of 4 is 1. So I did still kind of work those out. Now, again, to put all this together to get my answer, I'm going to multiply straight across. So I'm going to multiply this coefficient by this and by this. And so for that first row, that would be 1 times 81 m to the 4th times 1. So that's 81 m to the 4th, obviously. In the second row, I have to multiply 4 times 27 m to the 3rd times 1. And so 4 times 27 gives me 108, and I have that m to the 3rd. In this row, I'm going to do 6 times 9m to the 2nd times 1. So 6 times 9 times 1, that makes 54, and I have m to the 2nd. In this row, I have to do the 4 times 3m times 1. And so 4 times 3 times 1 makes 12, and I have just an m. In the last row, I got to do, again, I know it doesn't really matter, but just to show you that it is still what I'm doing, 1 times 1 times 1 means my last term here will be 1. Now, putting all this together, I could identify if it wanted me to tell you what's the first term, what's the second term, what's the third term, what's the fourth term, what's the fifth term in the expansion of that binomial, or I could list out what the whole expansion is. I'd say it's 81m to the 4th plus 108m to the 3rd plus 54m to the 2nd plus 12m plus 1. And again, I know it seems like a really long process, but I promise this is still somewhat faster than actually multiplying that binomial out by itself 4 times.